I remember the words well. He said, "It will not surprise you that we're giving the Nobel Prize in Physics this year to you for your contributions to LIGO's discovery of gravitational waves." I said, "It doesn't surprise me at all, but I'm very disappointed. It should have gone to the entire team."
Right.
And I would have thought that after the experience with the Higgs boson, where you did not give it to the entire team, that you would have figured out the importance of educating the general public about the necessity and power of large collaborations and things like this. And he said, "Well, we can discuss that
At the
when
dinner.
you're in Stockholm."
Hey, Kip, how are you?
Good. How are you?
Good. This is Priscilla.
Hi, Priscilla.
Kip, thank you for doing this. I appreciate it.
Happy to.
You know, Kip, when you think of the world and all the things in it, you know, and you think of science, like how do you visualize it in your mind?
Just
You know?
jump right in. We just jump
Well,
right
well, no, but it's like, you know, because you're working in gravity, you're working on all these super complex things. You understand theory of relativity, but you know, like I sort of have a glimpse of that in some very primitive way. But how do you think of it?
Well, I visualize things in a visual way.
Really?
Not in terms of equations. I'm not as extreme as Stephen Hawking was, that everything is geometry and shapes and surfaces in terms of his thinking and how he did mathematics. But visualization is a very powerful way for a physicist to think about the things he's doing. It doesn't capture all the mathematics by any means, but it captures the essence.
So if you're thinking about a black hole, like what does it
look like?
Yeah, what is
Yeah.
it? Is it something you're seeing in your mind that's spinning and things are disappearing into it?
No, well, it depends on what aspect of I'm thinking about. Usually I think about it as seen from a higher dimension, the shape of space, the warping of time in a color-coded sort of a way. And so I even draw pictures or have artists draw pictures for me that very accurately depict that. And that's the way I think about it.
Wait, do you tell the artist? Do you kind of work with the artist and say, this is the color and this is how it look like? How does that?
I generally draw a sketch myself. I'm not all that bad at drawing. I even took an engineering drawing class as a freshman at Caltech. Last year, this was required, something dating back to the 1920s, I think. But it was tremendously valuable. So I draw a very careful drawing typically of what it is that I want. And it captures the way I think about it.
No, a black hole is like a black hole, but it has all these different things going on in there that you've theoretically, that you've thought about. So how would you paint that? How would you draw that?
Well, for me, a black hole is, as I've learned from computer simulations and then taking the simulations and figuring out what's going on with pencil and paper equations. A black hole is something that's made from warped space and time. It has structure. It has things like arms and heads sticking out of it. We call these vortices and tendices. The vortices of twisting space stick out of the North and South Pole, a counterclockwise vortex out of the North Pole, a clockwise vortex of twisting space out of the South Pole. It has tendices that stretch things and squeeze things that are attached to it. If the black hole is colliding, these vortices and tendices go through gyrations and interact with each other and produce gravitational waves. So a black hole is a very rich thing for me. It's not just a hole in space, not just a black thing that just sits there.
But wait, for some folks that like myself, what actually is it? And I love that you have it. You personify it. So it's like a living, I mean, it's doing all these things, but what is it really?
It is an object that lives in the universe like a planet or a star or the moon, but it's an object that's not made from matter like you and I. Instead, it's made from warped space and warped time.
Now, whatever's happening in a black hole is not happening necessarily here on Earth. So how do you infer all these things that you just discussed, the heads, the tails, the spinning vortexes? How do you figure that out without, from where we're sitting?
You begin with Einstein's laws of physics, his laws that describe the warping of space and time. You manipulate them. I and colleagues manipulate them, sometimes by hand on equations, sometimes in computer simulations. You see what they predict, you see what they describe. And then just to make sure that what you're doing makes sense, wherever you have any observational data, you check it against the observational data, which is what we do with LIGO. When we see black holes collide, we get gravitational waves out that stretch and squeeze our gravity wave detectors. And you check that the predicted shaping of the stretch and squeeze, how the pattern, this time passes of stretch and squeeze, that it corresponds very precisely to what Einstein's laws predict. And then that gives me confidence that the things that I'm extracting from those laws through simulations and manipulating equations, and those things are right. And then we visualize those things as I've been describing.
So when did you meet Stephen Hawking?
We met in 1965. I had just completed my PhD earlier that month. It was June of 1965, late June. And there was a conference on general relativity in London. So I went there. I knew of him because of his seminal work, his very earliest publications. And there was a rumor he was going to give a seminar about what he was thinking about applying Roger Penrose's techniques of topology to describe the birth of the universe. He was going to give that seminar in a particular room. And so I went there. It was a packed room, a small room, probably seated maybe 20 people, and there were probably 50 people in the room. And he was at the point where he was at that time sort of walking with a cane, but he was walking, and his speech was fairly understandable. And he gave a talk at the blackboard. I spoke with him afterwards out in the hall, and we became friends over the coming few years.
Did you guys recognize something in each other? Because you're both, you know, exceptional at what you do. So was there a kindred spirit when you met?
I don't recall at the very beginning, but fairly quickly we found that we had similar views on life. We became close as people rather than as physicists. I never wrote a technical paper with him. We never collaborated on research, though we occasionally did work in parallel and exchanged ideas and argued and debated. But almost entirely our relationship was a personal relationship.
Kip, what was your, you know, as a little kid, when were you getting interested in all of this, in physics and the universe and all? Like, what are your earliest, you know, kind of memories of getting you into this work?
Well, as when I was a little kid, up to age 8, I wanted to be a snowplow driver. That was the most powerful job there was in the world. You grow up in the Rocky Mountains.
Yeah.
And you have the kind of winters we had in 1948. But then my mother took me to a lecture for teenagers about the solar system by a professor of geology at the local universities. I became absolutely enamored with the idea of the solar system. And my mother then sat down with me and we made a scale model of the solar system together. She showed me how to compute, to scale the solar system down so that if the sun was a 4-foot circle on the corner on the sidewalk in front of our house, then how big was the Earth and how far away was it? And the Earth was down toward the end of the block and Pluto was out in the next town. And it was teeny. And that blew my mind.
You know, now
Yeah.
she was an economist. So where did she have this background in cosmology?
Well, she was just a smart person. She didn't have the background in cosmology, but she knew she could go to, not online, but go to a book and find out the dimensions of the solar system. And she was smart enough to know how to scale that down to a 4-foot sun and just showed me how to do it. And I sort of absorbed how to do it as an 8-year-old kid. But I mean, she had this skill with all of her children to help them find something that really interested them and then to help them initiate projects. And I took off after that without much further help from my parents.
But she visualized it. She showed you that's how you said to Jesse, you kind of think of things. Also the idea of relativity, that Pluto's in the next town, right? What was the furthest thing out, by the way, in that first?
Well, that was Pluto, because we didn't go beyond the solar system, and Pluto was the most distant thing that we knew of in the solar system at the time.
Now you've had over 50 PhD students, you know, get all the way to the end. Now, do you think that some of that giving that knowledge comes from, you know, your mom, like the way to teach and to give? Is that a reflection of her?
Well, I think maybe to some degree, certainly she was the first person to inspire me. Well, my father as well, he was a scientist, he was a soil chemist, but she was the one that got each of the kids started on whatever project they were interested in. But no, I think the more I was inspired in my methods of working with students and mentoring students were inspired more by John Wheeler, who was my PhD advisor, and J. Robert Oppenheimer, who was known as in some sense, the father of the American atomic bomb. But I knew him. He was the director of the Institute for Advanced Study in Princeton when I was there in Princeton as a graduate student. And he was a very inspirational man. And I talked to people who had watched him mentor students. I read about how he mentored students in the 1930s as he shuttled his research group back and forth between Caltech and where I became a professor in the University of California at Berkeley. And his style of mentoring students as a group and having them mentor each other was very inspirational for me. So I patterned my ways largely after him, after John Wheeler, after Robert Dickey, who was an experimenter. And there also ran large research group, and I watched how he mentored his students.
Now, John Wheeler, he challenged you to think about, I don't quite understand it, about the cylinders and gravity. Like, was that the first challenge that got you on to thinking about black holes?
I tried to understand black holes. They were not called black holes yet. They were a particular solution of Einstein's equations called the Schwarzschild solution. I tried to understand it as an undergraduate, just reading. And I was just totally flummoxed.
Happy to hear that, just want to say.
Well, let me just also say that when the earliest work on this was done by Oppenheimer, in fact, in the 1930s, Oppenheimer and his student Hartland Snyder, who had been a truck driver in Utah, by the way, where I grew up. Anyway, Oppenheimer and Snyder wrote the seminal paper on black holes. And the two probably greatest physicists of the time in Russia, Lev Landau and Yevgeny Lifshitz. Well, I knew Lifshitz really well later in life. And Lifshitz said to me, you can't really appreciate in the modern era how completely difficult it was for us to understand what was going on in this black hole work, the seminal black hole work of Oppenheimer. You look at the equations, we tried to understand what the equations were saying, it just didn't seem to make sense. Everybody was really in a quandary to try to understand this in the early years.
So, you know, at the LHC, you know, at the Large Hadron Collider, you know, they found the Higgs boson. It didn't work exactly the way they thought it would, but they found it. But before they did that, they had to test every bit of what we understand around physics in order to tune the machine so that they would know if they actually discovered anything. In LIGO, you don't have that opportunity. So you have to design all these instruments to measure these calculations without being able to test them before you actually build this, you know, billion-dollar machine. So how do you think about that at the beginning? Like, what's even the first thought about this experiment before it's even all the stuff comes out? And then how do you sort of think about how you're gonna do it?
Well, you begin with Ray Weiss, and more than anybody else. So there was earlier independent work by others, but it was just the germ of the idea. So it was really Ray Weiss at MIT who had the full idea in all its glory and who explored it. And the idea was using this technique we call interferometry to detect a gravitational wave. But the idea that the wave stretches and squeezes space, and therefore if you hang mirrors from overhead supports some distance apart and a wave is oscillating faster than the 1 cycle per second swinging of a mirror, then it would just move the mirrors back and forth relative to each other as though they were not suspended at all. And so he had this idea that you want to measure the motion of these mirrors hanging from overhead supports. You do it by bouncing laser beams in between them. But then to get high accuracy, use the same technique as Michelson and Morley did back around the beginning of the 20th century to search for an ether to see, and this technique of interferometry, that the gravitational wave squeezes along this direction when it's stretching along that direction, and it does it in oppositely on perpendicular directions. And so you send light down, trap it between mirrors in one arm, between mirrors in the other arm, let it bounce around, back and forth a few times, and recombine it. It interferes, and you get an intensity of light that just goes up and down proportionally to the stretching and squeezing of space. So that basic idea of Ray Weiss's, and then his identification of all of the major, the biggest, most serious noise sources you would have to deal with, and his ideas for how you dealt with them, and his resulting estimate of how good these instruments could be. That was what he gave us in 1972. And it was really a really remarkable tour de force. And so, no, we didn't have tests. We knew the basic idea, which is very simple, stretching and squeezing out of phase along perpendicular axes, interferometry to observe it. And so you could be off and running and designing an instrument, trying to identify all the noise sources. And once you had built an instrument, you could actually test it by making the mirrors move apart and together, just like a gravity wave would with electrical forces. And so the whole thing was certainly at first sight straightforward, but not really straightforward, because the number of things that could go wrong, the number of things that could disturb the instrument were so enormous that the instrument in the end had to be horrendously complex in order to deal with everything that could go wrong. And that was where the challenge lay.
Now, how big are the mirrors inside LIGO?
So the mirrors currently inside LIGO are 40 kilometers. So I forget precisely, but they have a diameter of about 30 centimeters, if my memory is right. And they're maybe 20 centimeters thick or so, something like that.
And how far do they have to be from each other to really understand what's going on?
Well, you'd like them to be more or less as far apart as possible, because then they're moved more. The closer together they are, the smaller the motions. And so we chose 4 kilometers for LIGO, just because that was about the biggest thing that we thought we could afford. And it wasn't easy to find sites that could handle something that were flat and level, or could be made flat and level with a reasonable amount of earth moving, where you could get bigger than 4 kilometers.
Now, how long did it actually take to construct LIGO?
The actual construction began in 1995. The facilities were all finished by about 99, so it took several years. And then I began to install the interferometers. From the outset, we said, when we proposed to build LIGO in 1989, in the proposal of the National Science Foundation, we said we would have to likely have a couple of generations of instruments before we would see anything. If we were lucky, we would build a first set of gravity wave detectors and see something, but more likely than not, we wouldn't see anything. But we had to do it in 2 steps, because building something that would have a high probability of seeing anything, that was so complex. We had to get our feet wet by building a simpler set of instruments first.
So it took 10 years to get the thing built?
So the first instruments we began installing, I should say the experimental team, and I'm just a theorist associated with it, began installation in about 2000. They were operating near design sensitivity by about 2006. And they collected data from then to 2010, didn't see anything. In the meantime, the advanced interferometers, the second generation, was in preparation through the 2000s. And in 2010, the first interferometer shut down, and the advanced ones, which we thought had a good chance of success, or the early ones, it would be a long shot. We began the installation of the advanced ones in 2010. First search for with the advanced ones was in 2015, and the waves came in about 3 days before the first search started.
So where were you when you heard that it worked? After having worked on it for 25 years, you just turn the thing on and all of a sudden you can't stop it from collecting.
So I would reemphasize that it wasn't me, it was the experimental team. I was just a flaky theorist associated with the project.
Sure,
I
but you
did-
must have, I bet you got a call, no?
So an email. I got up every morning and get up and look at my email. I had an email from Christian Ott, a young guy at Caltech who was working on LIGO. He said, look at such and such an internal LIGO collaboration website. We may have seen gravitational waves. I looked at it and the computer had analyzed the data, all pre-programmed. It's seen the signal in the data, had analyzed it and had details of the signal there. I looked at it and it was too good to be true. I was skeptical because it was too good to be true.
And then now, how many signals has it seen? It's seen a lot of signals.
So the third catalog was just released the day before yesterday. And it's now up to just shy of 100 signals. It's,
Wow.
I don't remember the precise number, but it's say around 90 signals that we've been seeing.
When you were in the 90s, saying you had to write these proposals, how are you trying to explain to people to get the funding and to get the buy-in what it is that you were looking for? Because it hadn't even happened yet. How did you kind of navigate that process?
Well, I think the issue was to describe the vision for what this could do. And the vision is just totally compelling. I mean, the issue was, in retrospect, I say it better than I did at the time, but it wasn't far from this, that according to the laws of physics, there are only two kinds of waves that can travel across the universe, bringing us information about what's far away, like gravitational waves and electromagnetic waves. And Galileo started modern electromagnetic astronomy by building a little optical telescope pointing at Jupiter and seeing its four moons. And we know a lot happened after that. And we wanted to do what Galileo did for the other kind of wave, the gravitational waves. And just as electromagnetic waves had revolutionized what we understand about the universe, so gravitational waves will too. That was the basic message, but it went beyond that to talk about black holes, colliding neutron stars, the very things that we've seen, black holes swallowing neutron stars, which we've also seen, and other things that we are likely also to see in the future as concrete examples. But then the fact that whenever a new way of observing the universe has been opened up, and this has happened a lot in my scientific career, going back to the 1950s, the 60s, there has almost always been huge surprises. And these huge surprises could themselves revolutionize our understanding of the universe. So that was the basic message. And so that was not hard to sell. The issue is whether or not the experimental team could pull it off. How strong are the waves? What sensitivity can you expect to get? How much is it going to cost? That, of course, was where one really had to focus in. And I think a very crucial thing about how we did it was being absolutely honest about the odds of success. We said in our proposal, the initial interferometers have a shot at seeing something, but likely will not. And you're going to have to go beyond them. But we have to do it in 2 steps. And had we not done that, when the initial interferometers saw nothing, we could have been shut down. But in fact, the NSF and Congress, without batting an eyelash, basically, backed us to the hilt all the way through from the time that we were first approved for funding in the early 90s until we saw the waves.
Now, where were you when you got the call that you'd won the Nobel Prize?
I was at home.
Did you believe it?
Yeah, so I got the call from, I think, the Secretary General of the Nobel Foundation. And he said, I remember the words well, he said, it will not surprise you that we're giving the Nobel Prize in Physics this year to you, Rainer Weiss and Barry Barish, for your contributions to LIGO's discovery of gravitational waves. I said, it doesn't surprise me at all, but I'm very disappointed. It should have gone to the entire team.
Right.
And I would have thought that after the experience with the Higgs boson, where you did not give it to the entire team, that you would have figured out the importance of educating the general public about the necessity and power of large collaborations and things like this. And he said, well, we can discuss that
At the
when you
dinner.
Stockholm.
Although that does bring up the point that science is really becoming a team effort now, much more than it's ever been before, you know?
Well, some aspects of science, and this could only be done that way. There are other things that are still best done by a single individual or a small group of people. And so one of the great things that the physics community learned early on, going way back to the 1950s, I think, was how to maintain both small science and big science side by side in a collegial sort of a way. It's not 100% collegial, but it's amazingly with people who do big science and those who do small in the sense that it's just one person or a small group of people. Those who do small science, those who do big science, having respect for each other and understanding the importance of each other's work.
How important is it? You mentioned when you first met Stephen Hawking that you were debating and challenging each other. And so thinking about big science, small science, the importance of the questioning and pushing against, like, how do you learn as a scientist to debate and to argue? And, you know, it's a lot, we're losing that as a skill, I think, that critical thinking. What do you think about that?
Well, I don't know that we're losing it in physics anyway. There is a real issue in society.
Yes.
It's a collegial give and take. But in science, at least in physics, I don't think things have changed particularly. When a young person learns how to do research, it's generally in a research group. Different research groups have different styles, usually driven by the mentor. In some research groups, there's a lot of debate and give and take. In others, there's much less so. I have colleagues, superb scientists, who say to their students, it's a rough world out there. We've got to toughen you up. My attitude is quite the opposite. And it came from John Wheeler. The exploration of the universe is a wondrous thing. Whether you've got a tough character or a soft character, it doesn't matter. You can contribute in major ways. And if you find the ways to contribute that are controlled both by your talents and by your personalities. And so there are different styles in different research groups. And I do see that people who are trained in different research groups, they come out with different styles, different ways of interacting. But the community, at least with physics, again, functions very well with different kinds of personalities contributing in their own ways.
I think that probably has a lot to do with if the other group doesn't see that the experiment worked, it has to be validating on both parts. You come up with an idea and then somebody else has to see it or else it isn't adopted. Yeah.
Oh yes, absolutely. So as a community, you have to be tough in terms of maintaining standards. Absolutely. But in terms of mentoring young people, getting them started, you will certainly educate them about the necessity of validation through experiment, through observation, validation through other people doing an analogous calculation. These things are important. But when you're doing your creative work, don't worry about that in the early phases. You want to sort of be a free spirit and really be able to explore and search. But then once you think you have something, then you start getting rigorous and making sure to dot all the I's and cross all the T's, as one says in writing.
Did you see that with Feynman because I imagine you guys were colleagues for a long time? Did he have that imagination?
So Feynman was a very interesting character, and we were close personally. He was a man who displayed enormous insights and imagination, and he saw things that other people didn't see. But it turned out he saw them because he was driven by his own intellectual curiosity, and like as not, he had previously thought about something that in his own calculation satisfied his curiosity and set it aside, moved on to something else. So a good example, when quasars were first discovered, these are the most violent events in the universe aside from the Big Bang that we've seen until we saw gravity waves, huge explosions in the nuclei of galaxies. When they were first discovered, people were trying to figure out what they were caused by. And there was a theory devised by Fred Hoyle in Cambridge and Willie Fowler at Caltech that they were powered by supermassive stars, extremely massive stars that weighed, say, 100,000 times what the sun weighs. And so they gave a seminar about this at Caltech. I wasn't there. I was by then a graduate student at Princeton. So I just knew about this from people who had been there. In the middle of the seminar, Feynman stands up and he says, hey, your theory has problems because these massive stars that you're talking about, they're going to be unstable and collapse because of the effects of relativity. And people were rather flabbergasted. Nobody had ever talked about any instability generated by relativity. But it turned out Feynman was right. Chandrasekhar at Chicago, within a few months of that, published an analysis exhibiting this instability. That relativity would take massive stars just because of their properties and cause them to implode. How did Feynman know? I mean, it was seen as Feynman's brilliance, his just deep insight. So I asked him, and he said, well, I did the calculations. And I said, can you show it to me? He brought into me 40 pages of hand calculations. He'd been motivated by John Wheeler, who was his mentor and mine, and was talking about gravitational collapse to form black holes. He'd been motivated to ask himself about the instabilities in stars and how they would implode to form black holes. And he worked out the equations. He solved them numerically because he couldn't see quite how to solve them with pencil and paper. He solved them numerically using a slide rule for a few steps to see the onset of the implosion. And this was all in these 40 pages of calculations. He never told anybody about it. He just did it because he was curious.
Yeah.
And set it aside. And when the seminar came, well, he knew the answer. But this was a man whose reputation for his insights was so huge. Those insights were like as not based on hard work, driven by his own intellectual curiosity. Quite amazing man.
You know, there've been so many people at Caltech, you know, Murray Gilman, you know, all these guys that you've had down there, and I imagine women too, you know, do you think that circle of people has pushed each other forward?
Certainly to some degree, absolutely. But I think the key thing is that at Caltech, there has been a community of people on the faculty who value great science and who have worked to maintain and continually build the faculty so that when exciting areas arise, you move into them and you close down old areas that are less exciting. And this process of renewal without growing the faculty very much has been uniquely strong at Caltech. And the process of having high respect for what your colleagues do in very different areas of physics, say, and doing what you can to help maintain an intellectual environment that is really stimulating for everybody. It's central to the culture, and it's just superbly good at Caltech.
Did you meet Carl Sagan down there?
So I knew Carl Sagan quite well again. He was coming out to Caltech in the 1970s for planetary missions. That's probably where I first met him, but I also started spending time at Cornell in the 70s. And so I knew him both at Caltech and Cornell, and we became good friends too.
You know, in Contact, which is a movie I think you worked on, you know, the big ball drops through the I don't even know what you would call it, and Jodie Foster is transported to the other side of the universe and then comes back in a split second. You know, is that what is that? Is that something that there's a theoretical idea behind? Is it time travel? What is that?
Well, that is a wormhole. Contact began as a screenplay that Carl wrote, that I think he may have written it with Annie Dryan, who was his wife. I don't remember for sure. Certainly they wrote together later. Anyway, he wrote the screenplay and the movie didn't go anywhere. This was in the 1980s, early 80s. So he turned it into a novel. And then about the time his novel came out, the movie started to take off. So he sent me his novel for me to comment on. And he had his heroine, Jodie Foster, in the movie. I go through a black hole to get to the vicinity of the star Vega. And I told him you have to use a wormhole, not a black hole. And so he changed the novel in the page proofs, which his publisher was not happy about.
Yeah.
And then, anyway, so then the wormhole became central to this. But in the making of the movie, George Miller was the director, and I was only consulting just a little bit on it. It was really Carl, and Linda Oakes was a producer. And we were just trying to figure out how to handle the wormhole at the end when the studio got fed up with George Miller for taking too long to perfect the screenplay and not get into production. And canned him, brought in Zemeckis with an order that you close this thing out. They closed it out. And so they didn't depict anything about the wormhole. You saw what you saw, which I didn't think much of.
You
Now,
know,
did
It was supposed to
Interstellar,
be, it was supposed to be a wormhole.
now did Interstellar, start the same way?
Oh, no, Interstellar was completely, well, it was the same way in the sense that Linda Opes and I started Interstellar. Carl Sagan, and then with Linda as producer, started Contact. So it was the same producer. And so we started Interstellar. And just as Carl built science from the ground up, embedded in the screenplay, I embedded the science in the Interstellar treatment that we wrote. And then the treatment wound up in the hands of Jonathan Nolan and Christopher Nolan, turn it into a screenplay. But the science was built in from the beginning.
how important is it, Kip, do you think, these are two seminal films that to bring these ideas that are really complicated into this, for the public, for a broader group of, humans to understand, like, how did you feel about, wanting people to understand in a different way, in an emotional way, in a, visual way? How important is it? Because like I said in the beginning of this conversation, there's something I don't really understand a lot of what you do, but the importance of bringing the imagination to the public to understand why it's important.
So the idea of this movie, the very first step was Linda calling me and saying, "Would you like to brainstorm with me for a movie?" And I thought about it for a few milliseconds and said yes. But my motivation was, one, that it would be fun, and two, that a movie like this could be very powerful in inspiring people about science. I think that's very important, to provide inspiration about science and to display science in action and the power of science, the beauty of science. So that was the goal from my point of view, and a goal that was embraced by the Nolan brothers, who completely changed the story that I began with, but kept all the science, and then in interaction with me added more science as they modified the story.
So, Kip, you've been working on LIGO for a very long time, and you've seen these discoveries at the LHC, and, we're going to have these discoveries on neutrinos. Where do you see science going in the coming years? What do you think the next things to be explored are?
I don't have great wisdom about that. The thing that I really want to understand, and that I think we have a good shot at in my lifetime, I should say, I plan to live for another 29 more years. I'm 81, I'm aiming for 110. So
Yeah.
the thing I'm expecting by about 2050, which is when I plan to die,
Yeah.
is an understanding of the birth of the universe, the laws that govern the birth of the universe, which is the laws of quantum gravity. And I think the key to this is the theorists are working very hard, and have been, is the holy grail of theoretical physics since, I would say, the 1980s, at least, if not earlier, to understand these laws. We don't have very much observational data to provide guidance, but I think that those observational data, at least some observational data that could be very powerful, will come with gravitational wave observations of gravitational waves from the Big Bang.
Now, is the difficulty of that, Kip, that we can't see back before the Big Bang, and we can't account for the energy that's in the universe now?
Well, the difficulty is just saying to the Big Bang. I don't think we'll ever see back before the Big Bang, though. Roger Penrose argues that there are imprints of what came before left on the universe today. But the Big Bang itself was almost certainly controlled by these laws of quantum gravity. And if we can see what came off of the Big Bang, and we can see it in several very different frequency ranges for gravitational waves, which is what I expect we will have by the middle of this century, then that may give us enough data about how the laws of quantum gravity crafted the Big Bang that we'll be able to simultaneously crack the issue of the nature of the laws of quantum gravity and how the universe is formed. That's the dream anyway.
Now, Kip, why do we as human beings, want to look back into the very origins? Why do we write symphonies? Why do we, what is that thing, that quality of human beings that always has them pushing?
And I think we're born with it, and it's innate to the human race. And I often like to cite the issue of what do we see as our legacy. that our ancestors brought to us from the period of the Renaissance. And I think most everybody agrees it's great art, great architecture, great music, and the scientific method. And these are cultural things, including the scientific method is really a cultural thing. It's the foundation for technology, yes, but it's the scientific method is the thing that gives us the ability to understand how the universe works. And so this culture is really important to us. It's infuses education that I grew up with, and I would hope is infusing the education that current generations grow up with throughout the world.
Yeah.
Do you think that, if we think about the universe in these terms that you're talking about, it also gives us our understanding of our own place in it, which is very small, so that, it's a humbling, and we should be, understanding that things don't revolve around the I, the individual. Do you think about that?
Well, I think about it, but I don't know that our place is very small. Certainly the Earth is very small as a part of the universe, but the future of the human race could be very big if we don't destroy ourselves before we get there.
Kip, thank you very much for spending time with us today. I really appreciate it.
It's a pleasure. Thank you,
Yeah.
Jesse.
So much. Thank you.
Lisa.
Well, what can you say? I think he said it all.
I think you said it all. I'm not sure there's anything else.
Okay, I'll see you on the next one. Okay, where we'll be discussing, bird migration paths or something like that. Okay, bye, you guys.